So let us start a new chapter today. We shall talk about voltmeters, ammeters, ohm meters, etc. Okay.
Sir,
Yes.
sir, I actually had a question regarding the previous topic. Sir, in the electrostatic
Hmm.
instrument,
Hmm.
sir, actually when we connect a capacitor with a voltage source, half of the energy is lost now because the capacitor stores half CV square and the voltage source supplies CV square. So half of the energy is lost. So when you actually proved the torque expression for electrostatic
Hmm.
instrument, you didn't consider the loss. So.
Mm. Acha, can you kindly remind me this question around 1250 or 1245?
Okay, sir. Okay, sir.
Okay, fine. Acha. Ammeters measure current, we all know, and suppose we have any circuit, any random circuit you can think of. And suppose you want to measure the current through this resistance. What do? We break this connection here and put an ammeter, and this can be a PMMC instrument that we have studied, or it can be a moving iron or a electrodynamic instrument, and all of them we have seen that their deflection depends on the current flowing through the coil. So when you connect this instrument, the coil of the instrument in series with this branch, then the current I will flow, and from the deflection you can measure the current flowing through this branch. Okay. So all these types of instruments by default they work as ammeters. Now there is a catch here. The catch is that the moment you inserted the instrument in the circuit is changed. The circuit is no longer as it was before the instrument was inserted. Therefore, this current I can also change, and therefore the reading that you are getting is denoting, is showing the value of the current which is flowing now in the presence of the instrument, and this may or may not be same as the current that was flowing before the instrument was inserted. So when the meter is inserted, the current may change, and that may cause some error in our measurement. Now therefore we would like that this current is not changed much, and for that we need the impedance or resistance of this meter to be as small as possible, to be very small, so that when you add this instrument, this current is not changed. Ideally, if the resistance is 0, if the internal resistance of the ammeter is 0, then this acts like a short circuit, and then it is not changing the circuit, so current will remain same. So ammeters must have very small internal impedance or resistance. Okay, now the question is, when I say very small, this is a incomplete or a vague statement, because how small is small enough? How small will be sufficient for my purpose? So that is the question. How small should it be? Should it be smaller than 1 ohm, 1 milliohm, 1 microohm, 1 kiloohm? What do we mean by the resistance should be small? Okay, to answer this question, we will use Norton's theorem. So consider this circuit as seen from these two terminals. Okay, let me call it AB. Okay, so consider, so look at the circuit from terminals A and B. Look from terminals AB, and we know that then this remaining part of the circuit can always be represented by a current source in parallel with a resistance. Okay, this comes from Norton's theorem. So this is the Norton's equivalent. These two terminals are AB, and the value of this current source I, this should be equal to the short circuit current that will flow from A to B, short circuit current between AB and this resistance, let me call them IN and RN. Then RN is the resistance between A and B. I mean resistance of the circuit between A and B. Okay, you can say open circuit resistance. Fine. Achha. Now, in the original circuit, this branch was shorted and current I was flowing. So this current was equal to IN in the original circuit. So this is IN originally, and this is the current that we want to measure. We want to measure. But to measure this current, what have we done? We have inserted the ammeter here. let me write A for ammeter. Okay, and now say the current that is flowing is I prime, and this is the value that we are measuring. This is being measured. So we wanted to measure IN, and this is what we are actually measuring. Now the question is, are these two equal, and if not, how much is the difference? Okay, now how much is I prime? This value, the value of I prime will be equal to, we can use Norton's theorem now. Suppose the resistance of the meter is RA. Suppose RA is the ammeter resistance. Then current I prime, which is flowing now, is given by IN, this current, divided by Rn plus Ra, Rn plus Ra, multiplied by Rn. This is current divider rule or Norton's theorem. Now, is this equal to In? Of course not. These two are of course not same. Okay. So we wanted to measure In, and we are measuring this value. So how much is the difference? So how much is the error? Error will be the difference between these two. So In minus this quantity this is the error, and percentage error or relative error will be this error divided by the actual value. So this is percentage error. Okay, you have to multiply with 100. Achha. Then this In, everything cancels, and we have 1 minus this quantity. So that will become Rn plus Ra minus Rn divided by Rn plus Ra into 100 in percent, and then this cancels, and this is what we are left with. Achha. Now this I will write as 1 over 1 plus Rn by Ra into 100. Now we want this to be small. We want this quantity to be as small as possible. So we want this denominator Rn by Ra to be very large. So we need this quantity to be very large. That means Ra much smaller than Rn to have low percentage error. Okay, so this gives a better quantitative assessment on how small the resistance of an ammeter should be, and the answer is it should be much smaller than the resistance of the circuit that we are measuring, as seen from the terminals where we are inserting the ammeter. Okay, so this is a quantitative assessment of how small the ammeter resistance should be. Now, if I tell you that I want this error to be smaller than say 1%, then you should be able to calculate how large or how small Ra should be compared to Rn. That you can do. I will leave that calculation, those kinds of calculation for you as a homework. Okay, next let us talk about multi-range ammeters or range changing of ammeters. Suppose I have an ammeter and we say that full scale deflection current, in short FSD, full scale deflection current of this ammeter is, say, something like 1 milliampere. What does this mean? It means if 1 ampere current is flowing through this meter, then the pointer will move to the extreme right position. It will show maximum deflection on this scale. That is called full scale deflection current. Now, if full scale deflection current of a meter is 1 milliampere, then we cannot measure more than 1 milliampere using this meter. But suppose we want to measure 10 milliampere. Do we need to use a different meter, or is there something we can do to this meter? Can we change something here so that this meter can also measure more than 1 milliampere? What do we do?
So shunt resistance.
Excellent. So to increase the range, we can connect a shunt resistance. Okay, so if this is my meter, I will connect a parallel or shunt resistance, call it RP, P for parallel, so that suppose we want to measure 10 milliampere, I mean up to 10 milliampere, then when 10 milliampere current flows through this arrangement, this meter will give full scale deflection. Okay, now the question is, what should be the value of this parallel resistance? Okay, so the question is, what should be the value of the parallel resistance such that this arrangement can measure 10 milliampere current? For that, we also need to know the resistance of this meter. Okay, suppose that is Rm, M for meter. Okay, suppose Rm, meter resistance, is given as 90 ohm, just for an example. Okay, then what should be the value of the parallel resistance so that this can measure 10 milliampere? How do we solve this? This is the way. So we want full scale deflection when 10 milliampere current flows through this arrangement. That means when 10 milliampere current is flowing through here, we want full scale deflection. And full scale deflection we will get if 1 milliampere current is flowing through the meter. That means remaining 9 milliampere should flow through the parallel path, parallel resistance. Okay, then we will get full scale deflection at 10 milliampere. Now we can calculate RP. How? Achha. So suppose this voltage is from here to here. If this is V, then we can say V is equal to 1 milliampere into Rm, and this is also equal to 9 milliampere into Rp. So that means Rp will be equal to 1 by 9 of Rm, that is, and Rm is given to be equal to 90, so this should be 10 ohm. This way we can change the range of an ammeter. Now if I want to make a multi-range ammeter, what can I do? I will take a meter and add a variable resistance in parallel. So basically this is one possible arrangement. So this is the entire meter, entire measuring instrument apparatus, okay, and the current that flows through here, that will be measured, and here you can see that we can connect, this is a switch, we can connect this to here or here, and accordingly the shunt resistance, parallel resistance can change and the range of the meter will change. Okay, now I can give you a question, for example like this, that the meter resistance Rm is equal to say 99 ohm, and full scale deflection current is 1 milliampere for this meter only alone, and I ask you that what should be the values of R1, R2, find R1, R2, so that we can change the range. We can have a range up to say 10 milliampere or up to 100 milliampere, etc. And of course we can easily get 1 milliampere if we do not connect any shunt resistance. If we keep it open, then we will get the full scale deflection current as the full range, that is 1 milliampere. So this you find out, that is your homework. Now this arrangement has a drawback. The drawback is this. Suppose you are measuring some current which is flowing, okay, so there must be some closed path, something is there, okay, let me not make it clumsy, and current is flowing, and while you are measuring that current you want to change the range of the meter. Suppose you were measuring this with 10 milliampere range or 100 milliampere range, and then you decided no, my current is of much smaller value and I want to change the range. So then you have to move this switch. But when you move this switch, you notice that momentarily both these resistances are not there. I mean, they are not connected for a brief moment. For a brief moment, no shunt is present at all. Then for that brief moment, entire current will flow through this meter only, which may cause some damage. I mean, if that is for a sufficiently longer time, that may be damaging. Okay, so for a brief moment during range change, no shunt is present. That is problematic. One way of solving this is as follows. We will modify our switches like this. So that when you move this switch, when this is changing its position from R1 to R2, for that brief moment it will touch both these resistances. Okay, so and after that it will touch only R2. So initially it touches only R1, then during the transition it touches both R1 and R2, and then only R2. So then there is no moment when the shunt connection is absolutely gone and the meter is safer. So this is called a make before break switch, which means make connection before breaking the connection. This is safer. There is another type of...
Excuse me, sir.
Yes?
Sir, I had a doubt, sir. Why are we using two resistors? We could also use variable resistor. In that case, only like changing, like this problem would be solved, right?
I mean, you cannot use a sliding rheostat if you are thinking that, because how will you know that which position is the perfect position? Okay, because the user is not going to measure the resistance and then use the ammeter. That is one thing. You can still do another thing, that is like possibly like this. You can have a arrangement like this. This can short this resistance or keep it open. Yeah, that is another way. I mean, this is not the unique way. So these two together is a variable resistance, and when you short it, then only this resistance is present. When you open it, both the resistances are present, so resistance changes. Yes, that is another way. Okay, but don't think that we will use a rheostat.
Sir, sir, since we are using different kinds of resistances in shunt for changing the range, sir, won't it affect the net current drawn from the circuit, because these resistances will also participate in the net impedance of the circuit? So there will be some change in the net current drawn. No? So what about that error part?
I'm coming. Before that, let me just tell this. So this is not a good idea because you do not know which position is which value. Okay, so this is not, this meter no one will buy. This may work only in laboratory. Okay, acha. Now coming to the other question. Acha. When we are adding these resistances, we said the resistance of the meter previously, resistance of the meter RA should be smaller than the resistance of the circuit. So what I was saying is that RA, meter resistance, should be smaller than the circuit resistance. Now, what is the meter resistance? What do I mean by the meter resistance? When I have an arrangement like this, then this entire thing is my meter. Not only this this coil arrangement, this coil is my meter, it is not alone, but the entire thing together is my measuring instrument. Okay, so RA in this case, okay, so let me write, where do I write? I write here, RA according to my previous notation is then this meter resistance Rm. I mean, this meter means this is only the coil resistance. Okay, coil resistance in parallel with this R1 or R2, whatever is there, are parallel. Okay, so this is meter ammeter resistance as a whole, ammeter as a whole. This could be the coil resistance only coil resistance. And this is the shunt resistance. So I was talking of both these in parallel together. That should be small. So this should be smaller compared to the resistance of the circuit between this and this terminal. Wherever I will connect this, between those two terminals, whatever circuit resistance appears, that should be larger, much larger than this meter resistance. Okay, that is the thing. And now if this Rm itself is small enough, then when you connect more parallel resistances, then it is even better. Rm parallel Rp will be even lower. Okay, so that won't create problem. That will be helpful maybe. And in fact, if Rm is not small, which is often the practically the case, Rm itself could be large, then the parallel resistance will solve the issue. Acha, okay, so I was talking about multi-range ammeters. Yeah, then there is another multi-range arrangement commonly used, which is like this. This is the meter, the coil magnet arrangement alone, and then we can have a number of resistances like this, and suppose this meter has meter resistance of say 900 ohm, full scale deflection current is 1 milliampere, and this is one terminal, and another terminal This is a movable key and this is the other terminal. So this is my entire meter. Okay, and let me call this R1, R2 and R3. This switch is movable. Now you notice that let me call this position 1, position 2 and position 3. In position 3, okay, we have R1, R2 and R3 together in parallel with Rm. So R1 plus R2 and R3, they are in parallel with Rm. Okay, then in position 2, we have R1 and R2 in parallel with Rm plus R3.
Rm plus R3.
Yeah, absolutely right. And in position 1, only R1 is in parallel with Rm plus R3 plus R2. So here you observe in position 3, parallel resistance is larger, so less current is bypassed, so less bypassed, whereas in this case lower resistance is in parallel, so here we have more bypass, so more current is bypassed in when the switch is in position 1. So that means in position 1 we will be able to measure higher current, so this will be higher range and this will be a lower range. Okay, now I have given you the values of meter resistance, full scale deflection current, and I can ask you the question that if we want the ranges as say up to 10 milliampere, then up to 100 milliampere and up to 1000 milliampere or 1 ampere, then what should be the values of these three resistances? R1, R2 and R. Yes?
Could you scroll up a little bit?
Fine?
No, I meant to scroll up. You scroll down.
Oh, scroll down. Okay. Yeah.
Okay, sir. Thank you.
Yeah. So now
Sir, your is covering half of the text. Video, sir, that patch.
Video. No, I mean here I can see the complete thing in my screen. I mean, what about others? Is it a problem in your locals?
Try opening comments. Then the screen shrinks so you can see full thing.
Okay, please follow the suggestion.
Okay, sir.
It's fixed?
Yes, sir.
Okay, thank you. Thank you, Saurav. Yeah. So now the questions are R1 should be how much, R2 should be how much, and R3 should be how much. Okay, let me give this as a homework. You can do it. At least try. If you have difficulty, then we will discuss later. Acha, fine. Okay. Okay, great. Next, before coming to voltmeters, I would like to answer the question that one student raised at the beginning of the class about the electrostatic instruments. Okay, his question was like this. So let me tell what he is asking about first, then I will answer. We know that if we have, say, a battery connected in series with a resistance and a capacitor, if this capacitor is C, voltage is V, resistance is R. Initially the capacitor is uncharged. Okay, and then if you connect this, then what happens? Current will come, current will flow, and this capacitor will get charged. Now at the final steady state capacitor voltage Vc will be equal to this battery voltage V. Then at steady state, energy in capacitor will be equal to half C Vc square, which is equal to V square. Okay, but now if you calculate the energy supplied by this this voltage source, so energy supplied by battery, how much is that? That will be this voltage into the multiplied by the total charge supplied. And how much charge is supplied? That is Q equal to CV. So CV multiplied with V, this is equal to CV square. So here CV square amount of energy is supplied by the battery, but finally stored energy in the capacitor is half CV square. So what happens to the remaining half CV square? That is lost.
Energy is distributed due to the resistance.
Excellent. So yes.
But even if we don't connect a resistor, still energy stored in capacitor will be half CV square, right? And battery will supply CV square. So where does that half CV square go? Means if we don't connect
at
a
the time of switching, maybe the timing of switching.
If there is no, okay, let me answer the other comment, the other question that was asked, and then I don't know whether time will permit today. If time permits, I'll answer this question, or tomorrow, otherwise, okay? One at a time, please. Okay. So in this case, remaining half CV square is lost in resistance R. And this you can verify exactly by writing differential equations, how current changes. We studied this in our previous Signet course a bit. So you can do that. You can write the differential equation, solve for how this current I varies as a function of time. Then you integrate this quantity I square R over time 0 to infinity. This will be exactly half CV square. Okay, this is fine. That this is a nice exercise that you can do yourself. Now the question that he is asking here, while we did this derivation for the torque, we did not consider any energy loss in a resistance or so. So let us revisit briefly what we did here. Here we assumed constant voltage, okay, and then we considered a small displacement d theta, okay, and constant torque, because this displacement is so small that within that small motion torque will not change. So that torque is T, which is a function of theta. T d theta is work done. Okay, increase in the stored energy, increase in stored energy is equal to d theta of half CV square. V constant, so I can write outside. Okay, and so these are the increase in energy, and this is coming from outside, and this should be, so let me write this R, because two things we are talking about, and this should be equal to the voltage between these 2 points, which is constant, okay, multiplied by the charge, excess amount of charge that comes here, okay, multiplied by excess charge coming. Okay, so we are talking from this, from the viewpoint of these two terminals only. We are not saying what is happening outside. Okay, outside these wires may have some resistance. Definitely they do have, and therefore the battery will have to supply more energy than that is entering through these two terminals. Okay, so the battery will definitely supply more energy. Some part of that will get lost in these resistances, and the remaining part will enter this parallel plate capacitor. We talked from the perspective of these 2 points, so we need not consider these resistances. Yes, you can do more analysis because of your better understanding, because of your interest. Then you consider how much energy is lost in these resistances, and when you add that energy with this energy, you will get the energy supplied by this battery, and you can verify whether that is coming equal to the energy as measured from these two terminals. Okay, that we did not do, that we also need not do. Okay, but for your interest you can definitely do. So the point here is these losses are not coming in the picture because we considered the voltage between these two terminals and the amount of charge that flows in or out through these 2 points. Okay, does that answer your query? Who asked this? Arpon. Yeah. Okay. Achha, fine. What was the other thing I said I will tell later? Something related to this.
Yeah, like
I
if we
see.
connect a
Sir,
battery
I see.
directly to a capacitor.
Yes, sir. I actually asked that only. I didn't ask about the resistance. I asked when we just connect a capacitor plainly to a battery, then also half of the energy is lost. Sir, where does that go? Because theoretically,
Okay. Let me see whether I can answer this today I'm also trying to think. Okay, acha. If you connect a capacitor directly and we want to say write the dynamic how current flows, etc. Let me see whether I can do it. If this current is it, this is constant, call it E, this is C, then at any moment if this voltage is Vc, then the current I is C dVc dt, this is the current. Acha. And but now I am in a problem. How do I write KVL? Because if I want to write KVL, I have to write E equal to Vc, and there is nothing else. I mean, no other voltage drop. But E is not equal to Vc. I mean, always it is not equal to Vc. It is getting charged gradually. Although it will happen instantaneously, theoretically in no time, but still it is not true. Okay, so even KVL is not true. So this analysis actually we cannot do in this way. And I remember I mean some other students also asked this question 2 years back, and then one of the students in fact actually found a research paper on this topic. Okay, and what they say, in this case the remaining energy will be converted into in the kinetic energy of the charge carriers, which could be electrons or ions, in this case electrons. Okay, so electrons also have can carry kinetic energy. They are moving, they have mass, so they are saying that I mean the only place where the remaining energy can go is the kinetic energy of.
Sir, once again, won't that kinetic energy be dissipated as heat when the electrons collide with the...
But how? If there is no resistance, if there is absolutely no resistance, then how that will be dissipated? But that is not a practical case, of course. I mean, even if there is no resistance, the capacitor plate will definitely have resistance. If you zoom in, I mean, if you zoom into these plates, electrons are coming and then they are getting distributed through the plate. There is resistance, of course that will get dissipated practically, but yes.
Sir, in the same manner, when we connect inductor to a EMF directly, in that case no energy is lost. So what is the speciality about the capacitor, that when it is connected charges are behaving in a different way, and why we are connecting an inductor, charges are behaving in another way? So means the inherent property of current is changing. So flow of charge just by some...
let me understand your question. Suppose you have a voltage source, you are saying, and we connect this to an inductor. Okay. Now what is your question? If this is V, if this is L, what will happen?
In this case, no energy is lost. Means energy supplied by the voltage source is equal to the energy stored in the inductor.
Energy supplied by the voltage source is equal to the energy VI. So in this case, what will happen? I will be equal to 1 over L times V, right? So that is because L di dt is equal to V, and V is a constant, so I will increase. So I will increase like this, okay, linearly. T. So that is the current, and now the energy supplied by this voltage source is equal to, so charge supplied Q qt, total charge supplied from time 0 to t, that will be integration of this quantity, so that will come out to be half. Okay, so this is the total charge. So energy supplied by battery, energy from battery, that is equal to the charge multiplied by the voltage, so it will become V square. Okay, acha. And energy stored in the capacitor, in the inductor, energy in inductor, that is half Li square, and I is here, so that will become half L, I will be V square by A square, V square by L square, T square. So this cancels, so we have exactly the same thing. Okay, so whatever energy is supplied by the battery, it is stored in the inductor. Absolutely fine. Okay, now what was your question here? I mean, what is the doubt?
So doubt is means how, means just changing some external component is changing the behavior of the means current or electron, that energy is dissipated in one case and the other in case of inductor it is not. Means why is it happening?
So,
I'm not considering a resistor in any of the cases, and means everything is same. Then why is it happening?
so may I suggest something?
Yes,
So-
please. Yeah.
So for the capacitor one, could you please move to the capacitor one?
Now.
So for when we switch on this circuit, so here there's something is different from the other circuit, that the inductor won't allow a sudden current to flow, because that's the property of the inductor. But in the capacitor, a current will flow, and
In
due
this
to the
case, current
Lenz's
will
law,
be impulse.
yes, and due to the Lenz's law, there will be an high opposite current that is observed in sparking. We usually observe that in sparking. So that may be the case of the energy loss.
No, sparking right now we will not consider, because I mean we will yeah, those are the practical situations. Okay, those are absolutely practical situations. Yeah, and in practical situations, sparking can consume.
Capacitor usually sparks when it is shorted, so that may be the case.
In
No.
this case, you are not considering anything, like, right? Means there is nothing, only a capacitor and an EMF. Theoretically, there is nothing. Then
Yeah, so,
why is it?
yeah, so Arpon is asking the question from theoretical perspective. Absolutely, because in theory, there is no need, I mean, in our thought experiments, we don't need to have any sparks. Sparks will definitely be there practically, but in thought experiments, we need not have any spark. So Arpon is asking this question from absolutely theoretical perspective. Okay, so I don't know whether what I'm going to say will help. Acha, by the way, since this is one, I mean, this is time is over. Those who have class, please feel free to drop out from the meeting. No problem. Acha. One thing that I will tell is this: think of a situation where we have a theoretical current source in parallel with a resistance, and this is my experiment. Here I have an inductor, RIL. Now if you connect this suddenly, then what will happen? Previously this current I was flowing through this resistance. After you connect this inductor will be a short circuit path for this current, and therefore this current will gradually stop to flow through the resistance, and it will flow through the inductor. So gradually this current will decrease and this current will increase. One thing which we can show, so we can show that finally the energy stored in inductor, so inductor energy, final L energy will be half Li square, but the energy that will be supplied by the battery after the switch is closed, not battery, I mean current source, energy supplied by source, that will be equal to double of that Li square, and energy lost in the resistance, energy dissipated in R, that we can show will be half Li square. You can write differential equations, solve for this current as a function of time, this current as a function of time, do the integration, and this you can do. This we can show. In fact, actually in electrical engineering, in circuit problems, always we may find, dual problems. Whenever we talk about voltage source, we can talk about a similar problem with a current source. Whenever we talk about a capacitor, we can talk about a similar problem with an inductor. These are dual situations. Okay, so this is a situation where we get something similar to this with a series resistance, which we talked. So this problem and this problem, they are dual. So if you think, if you have any uncanny feeling that why these energy equations, half energy lost, 50% efficiency we are getting for a voltage source capacitor business, why is it not happening for an inductor? There is definitely a dual situation which is like this. And now if I in this case, if I try to think what happens if I remove the resistance, just like you did here, you removed the resistance, you came to this situation. So we will be in this situation here. Now definitely let us see whether we still get some problem or not. So this should be problematic. Let us see. Should be problematic. Because the analogous situation here was problematic. Now let us see what could be the problem. I don't know. Let me check. One thing we know is when you connect it, I will be this I, and now L di dt, then that should be 0. So that means this voltage is 0. Okay, so this voltage is 0, and now if I want to write KVL, no problem, I can write. All I have to say that this voltage is also 0. Achha, so there is no problem in KVL. Will there be any problem in KCL or anything?
So if we are considering the current I to be a step function, in that case the voltage across this inductor, that will just simply be a spike, right?
That will be a spike. That will actually be delta T.
So how can we then calculate the power dissipated, or the power supplied by the source? So we are basically multiplying a delta function by a step function. How do you do that?
That is also difficult because delta multiplied with a constant.
So we won't be able to do that at the origin, right?
Yeah.
At the origin, we won't be able to do that.
At the origin, something is problematic here as well. Okay.
So this is the same thing which will happen in case if we short a capacitor with a battery.
if we short the capacitor with a
It's the equivalent scenario.
yeah, I mean
In every case, either the potential energy is stored or the kinetic energy is utilized. So there is no other scope for the other part. Therefore, this problem is happening. Maybe. So like in the capacitor.
yeah, I also have to think a bit. I mean, I don't want to make any strong comment without. But what you were saying, I can see that. I can realize that. But I mean, I don't want to make any strong comment without confidence at this moment. So let us all think about
Earlier,
it.
so earlier when we did the problem of inductor connected to a voltage source, and that problem didn't pose any problem. Energy conservation was maintained.
Yes,
Earlier
right.
when we are connecting the current source, then it is against may some problem may come like that.
Yeah, so, okay, let us check some problem. I mean, we expect it to be problematic. So let us see. So finally, finally inductor energy will be finally L energy will be half Li square. Now, what is the energy supplied by this source? Energy from source. That will be the product of voltage and current, and so first of all, the problem here is that if we do not have a parallel source, then this current has to be a step function, but that is not allowed.
So how do you calculate the energy? Like you cannot calculate the energy like this, energy from the source.
That is one thing. Yes, energy from, but also even before that, this is contradictory. Yeah, here this is contradictory because okay, I got a very good strong contradiction. Okay, the contradiction is this: call it I1, call it I2. I1 should be equal to I constant. That is the property of a current source. That is the definition of a current source. But I2 is I multiplied by UT. Okay? So, I1 and I2 are not equal. And if you consider KCL at this point, call it node A, so at node A, KCL violated. I was in fact expecting the KCL to be violated because in the previous case here KVL got violated, and since these are dual problems, so this was my expectation that somewhere KCL should be violated, and now I find that it is the case. And of course, what you are also saying, we will have problem in calculating the energy. Okay, because
sorry sir, but why will I1 be constant?
Because that is, I mean, constant in theory. Okay, that is the theory
Yeah,
of.
but even from that side, like the circuit is not complete. So even when like the switch is open, I1 should also be 0. So it should essentially also be a step function, right?
No, but that is not possible by definition of a current source. For example, by definition, you cannot. These are all theories. These are all maths. These are not practical. Okay, so that you must also have to keep in mind. You can never sort a theoretical mathematical voltage source, because then mathematics becomes inconsistent. Practically you can do, because definitely there will be some small resistance, but theoretically the moment you sort a voltage source, I mean, mathematics break down, because from the definition of voltage source, voltage should be V, but from the definition of short circuit, this should be 0. So mathematics will lift up the hand. I mean, we cannot apply mathematics here in that way. In the same way, we cannot keep a current source open. Again, then the mathematics becomes contradictory, self-contradictory, inconsistent. From this point of view, current should be 0. From the definition of a current source, current should be I. So we cannot apply maths anymore here. This is just theory. Practically, it has no.
Yes.
Yeah.
Same way, can we say like that we can't connect a capacitor directly to a voltage source because it will violate energy conservation? Like
Excellent, excellent. So if I have a capacitor with 0 voltage and a voltage source, you cannot short it. The moment you short it, here from this side it's 0. Yeah. Yes.
KVL would be violated.
KVL is violated. Also,
Energy
yeah.
will also be violated. So we can't do that theoretically.
Yes, absolutely. Mathematics completely break down here. I mean, I won't say breakdown. Breakdown is a negative word. I mean, these are I mean, mathematics are it's beyond. I mean, I won't say that it's a breakdown in a negative sense. It's not defined. It's undefined.
Thank you, sir. Thank you, sir.
Okay, bye.
Thank you, sir.
Thank you, sir.